the logarithmic scale. What is it? Why do we use it? And when do we use it? Okay, so what we're referring to here is, up to this point, we've gotten a lot of experience working with coordinate systems. Specifically, we've worked primarily with the Cartesian coordinate system. Shown here is a Cartesian plane. We've got the x and the y-axis. And the way you can think about this is you started with a real number line. And I say real number line because you could also have an imaginary number line, right? If you put an imaginary number line vertical like this, then you have the complex plane. That's all numbers that exist. But just thinking about the real number line, what you do is you take a real number line, put it kind of in the middle of the page, horizontal. Then you take another real number line, flip it vertical, and put it, kind of like at the center of the page, and then you've got a Cartesian plane where the two number lines cross is the origin. And you can do this same kind of idea in 3D. Here's x, y, z, and you create a 3D Cartesian coordinate system with three real number lines. Okay, now the number lines that we've worked with so far, and that that we work with the majority of the time, are what's called linearly scaled. Okay, so just the real number lines we work with, and I say real number lines, that you could think about this with even the imaginary number line. The imaginary number lines that we work with are linearly scaled most of the time. Okay, but we're focusing on the real number line. So, 1, 2, 3, 4. You got minus 1, minus 2, minus 3, minus 4. Right? So like this. This is a real number line that we deal with most of the time, and this is said to be scaled linearly. However, there's another way we could choose to scale this. We could choose to scale it logarithmically. And when it comes to, like a Cartesian plane like this, you could choose to scale maybe both the x and the y-axis logarithmically. Maybe you just choose to choose to leave the x-axis scaled linearly, but you scale the y-axis logarithmically, or vice versa. And it's the same idea with like a 3D Cartesian coordinate system. You could choose to scale all three of the axes logarithmically, or maybe just the x-axis logarithmically and leave the y and z-axis linearly scaled, however you want to do it. Okay, and so what does this mean to be linearly scaled or logarithmically scaled? And why would you want to choose to scale an axis logarithmically instead of linearly? Why would you choose to just maybe scale one axis logarithmically and leave the others linear? Well, that's what we're going to talk about in this video. Okay, well, let's draw two axes. On the left, we'll do a linear axis, and on the right, we'll do a logarithmic. So linear and logarithmic. Okay, so each of these is going to have a 0 point. And so this is 0 on the linear scale, and I'm not going to put anything on the log scale at the moment, at the 0 point. Okay, now, so for the linear scale, how do we normally set this up? Well, the typical process is you start by putting major tick marks. So there's major and minor tick marks. And the major tick marks are spaced more in line with the actual, looking at the computer screen here, or your piece of paper. Just a nice even spacing with respect to the poster board or your computer screen, right? So you do something like this, maybe. Okay, now we'll come to the logarithmic scale in a second, but let's focus on the linear scale. And so from here, what you do is you choose a common difference, which is represented by, like, what is the value at this tick mark going to be? So let's say this is 10. What you're saying then is there's a common difference between, or a common sum, however you want to look at it. When we go from here to here, we've added 10. And so therefore, if you go that same distance in the positive direction, you're going to add another 10. If you go in the reverse direction, you're subtracting 10. So if we go in the reverse direction here, we're subtracting 10. If you go that same distance in the reverse direction, or in the negative direction, you're subtracting 10, right? I'm assuming that I made these tick marks equally spaced. So there's a common difference. Okay, now in regards to if someone asked you, what's the common difference on this linear scale? I guess you would refer to what the difference is between the major tick marks. But in reality, there's no actual specific number for the common difference. But I guess that's how you could refer to it. But, you could also put minor tick marks. So assuming these are equally spaced, then the distance between these tick marks represent some fraction of the distance between the major tick marks that you add or subtract when moving that distance on the scale. So 2, 4, 6, 8, 10. So this distance here, if you move this distance, and when I say this distance, I'm talking like on the computer screen. Like you could measure this distance on the computer screen, and it's like a scale on a map, right? It tells you like 1 inch on the map corresponds to this many miles. Same idea. So when you've moved this distance on the scale, what is that, like 5 millimeters? If you moved in the positive direction, then you added 2 as far as the units of the scale to that starting point number. So you went this distance, so you did 0 plus 2. But this distance here that's consistent no matter where you are on the scale. So if you came here and you moved that distance, that means you added 2 to the starting point number. So you added 2 to 20 and got to 22. Or if you go in the negative direction down the scale, then you're subtracting 2 if you go that distance down from the starting number. So that's why I'm hesitant to say that, if someone asked you what's the common difference on this linear scale, I mean, there is technically no specific number, but one way you could look at it is you could say, okay, well, what's the distance between the major tick marks? That would be the common difference. Here it would be 10. So you could say that. Okay, but now there's another perspective that we can view this. And this perspective is actually going to be really helpful for understanding how the logarithmic scale works. So here is a plot of the line. So this is y is equal to 10x. The line that it passes through the origin, the y-intercept is 0, and the slope is 10. So you can see you go up 10 and then over just 1 to get back to the line. It looks like the line is like y is equal to x. That's just because I have the y-axis and the x-axis scaled differently. Okay, and so the way we're looking at this is the x-axis corresponds to the actual physical linear scale on the computer screen. And the way you look at the major tick marks here, this means you've gone 1 major tick mark in the positive direction along the linear scale. So what happens when we go 1 tick mark, we get to and this is the value, actual value of the scale. So you go 1 major tick mark, now you equal 10. You go 2 major tick marks, now you're at 20, right? You go 1 major tick mark in the negative direction, now you're at negative 10. Okay, and at this point, the major tick marks for both the log scale and the linear scale actually become kind of important. And so from this perspective, maybe it is best to say, look, the common difference of this linear scale here is 10. Okay, and the major tick marks are important because we're going to see with the log scale, we're going to start by drawing the major tick marks. And they can be spaced however we want. It's not like they have to have the same spacing here, but they're going to be equally spaced. Just like they were equally spaced here, the major tick marks are going to be equally spaced. However, the minor tick marks, we can space them however we want. We could make them equally spaced. We could do whatever we want. We're actually going to see the most common practice with a log scale is to have unequally spaced minor tick marks. But even so, still the major tick marks are equally spaced. And in that sense, even with a linear scale, you can space the minor tick marks however you want. Now it's almost always they're equally spaced on a linear scale because there's no reason not to do that. But you could space them cut it into thirds, right? 3 equal width pieces here. But you could, if you wanted to, we could space even on a linear scale. We could do like that if we wanted to. That's not a problem. But the way we're thinking about it is we're going to leave the major tick marks equally spaced and then doing whatever we want with the minor tick marks. Okay, so now coming back to this line here, you can see that when it comes to a linear scale, it makes sense why a line would represent a linear scale from this perspective. And I'm sure that's why it's called a linear scale. It's going to be any line, and the slope is going to be the common difference that you choose. And why does this make sense? Because the slope of a line is constant everywhere. So the idea is no matter where you are on the linear scale, no matter how far up in the positive direction or in the negative direction, if you go a specific distance along the linear scale, you're going to be adding or subtracting the exact same amount no matter where you are on the scale, right? If I go from here to here, that's, let's see, 1, 2, 3, 4, 5. I've gone 1/5 of the common difference, right? Going from major tick mark to major tick mark, that's a common difference of 10. I've gone 1/5 of that distance. So that means I've changed by 2. If I went forward, I went up 2. If I went back to the left, I went down 2. So here, that corresponds to up and down. The positive x direction here means I'm going up on the scale, right? The negative x direction here means I'm going down on the scale. So this distance here, no matter where I am on the scale, way up the scale, way down the scale, if I move this distance, I'm going to be adding or subtracting 2 to the starting number. Now, thinking about this from the perspective of the major tick marks, the way we look at this is, so you can have any linear axes with different spacing of linear tick marks. And when I say different spacing, I'm referring to, like actually on the computer screen, on the paper, how many millimeters are they spaced? You can have a different spacing linear axes with the major tick marks, but you could still plot it and still plot multiple linear axes on a graph like this, because the x-axis is from the origin to the first major tick mark, then from the first tick mark to the second tick mark. Because remember, on the log scale or the linear scale, the major tick marks are going to be equally spaced, and so it's always going to be from 0 to 1 is the distance from the origin to the first tick mark. From 0 to -1 is the distance from the origin to the first tick mark in the negative direction. And this works no matter what linear scale you're dealing with. It doesn't matter. It could be different linear scales with different spacings of the major tick marks physically on the page. It doesn't matter. Okay? But also, again, you can have minor tick marks can be equally spaced. They can be unequally spaced. It doesn't matter as long as the major tick marks are equally spaced. And so the way you look at it is, any distance traveled along the linear scale, you look at it as some fraction of the major tick mark distance. Okay, so if I move this distance, then you can see that on the graph it shows us that we've moved 2/5, because each of these 1, 2, 3, 4, 5, 2/5 of the major tick mark distance. So you could, if you were actually building a logarithmic scale, then you would know, okay, it's going to be, it looks like each major tick mark is about 20 millimeters apart. So you would take 2/5 of 20 millimeters, and that would be equivalent to what you moved here. Now, on the linear scale, we know that means that when you move that amount, that means that so 2/5 of 10 is 4. So that means when you've moved however many millimeters on the linear scale, you're adding or subtracting 4 to the starting number, right? You moved a certain distance up or down, so wherever you started with, you're going to be adding or subtracting 4. No matter where you are in the linear scale, that's going to be the case because the slope is constant. The slope of this graph is constant. Okay, and you see how you can, once you've got the major tick marks drawn, you can come to this first, going from the first tick, the origin to the first tick mark. You can set up what your minor tick marks are going to be with a graph like this. You could say, okay, I want to do, maybe you zoom in a little bit, but here it's easiest to see. We could do, okay, This would be at, so this is 2. 2, 4, 6, 8, 10. So you want to set up a minor tick mark at 2, and at 4, and at 6, and at 8. And you might say, well, isn't this kind of trivial? I mean, all I got to do that is just make them equally spaced from 0 to 1. The tick marks equally spaced, like, I'd measure this as 10 millimeters, so I'd go 2 millimeters for each minor tick mark. Yes, that is true. It's pretty intuitive for a linear scale, but I'm trying to kind of lay this out for you because it's a little more complicated with a logarithmic scale. Okay, but what you would do is you would say, okay, at 2, the value 2, I need to go, it looks like 1/5 of the distance from 0 to 1. Now, even if if you wanted to set up, if you wanted to, for some reason, put a minor tick mark at 1.2, or no, at 2.25, you would just need to do so do the inverse of this. You would say, if you know y is equal to 2.25, well, divide that by 10 and solve for x, and you get an x value. That would be what? 0.225. So you know that I need to go 22.5% of the distance from the origin to the first major tick mark. And so you apply that 22.5% to your actual physical measurement on the page. So what I'm saying is you can put minor tick marks wherever you want. Maybe you don't know the actual values maybe you know the spacing that you want. So you want to break it up into thirds. So this is going to be at x is equal to x equal to 1/3. And this is going to be at x equal to 2/3. And then you use the formula to see, okay, what's the y values at that tick mark going to be? What's the actual numbers I'm going to put on the scale at those tick marks? You can go in either direction, right? If for some reason you wanted unequally spaced tick marks, that's not a problem. If you know where you want them positioned, then you know the x value, the percent position you want them to be, and you could get, if you're going to do maybe a tick mark here and a tick mark here, then you can the position, you input that as the x, and you get the corresponding value on the axis on the scale you need to put. Or again, if you know the value you want between 0 and 10, if you want to do at 7.75, then you can still use the function, the inverse of this, so y divided by 10 to get the position. The position you need to put that mark to, and then put 7.75. Now, the way it works, something to note though is that once you have, let's say you set up your tick marks going from the origin to the first tick mark, then if you want that same pattern all the way up and down the scale between any two major tick marks, you can just copy and paste it. That same pattern will hold. And it's the same with a logarithmic scale. What I mean is, like, if you did, so here, we have it set up, this is 2, 4, 6, 8, then 10. We could just copy and paste these minor tick marks here, and it's going to be 12, 14, 16, 18. And this works out the exact same with the logarithmic scale. However, if you do want to think about, how this works, if you're not dealing with the origin and the first tick mark, like let's look at from the first tick mark to the second tick mark, then the way it is it's like, okay, if you want to look at see what position between the first and second tick mark is 12.5. So 12, there's about 12.5, okay? You would get that x value, let's see. So 12.5 divided by 10 is 1.25. The way you interpret this is you're going to be between the first and second tick mark here. It's 25% of the way past the first tick mark to the second tick mark, right? If we did this at 2.5, we would have gotten 0.25. So it's like you're 25% of the way from the 0 tick mark, the origin, to the first tick mark, right? That would have been 0.25. If you're looking at, okay, what about, what's the position of the negative 22, negative 24, negative 25. That's about right there. So what is that position? So you do negative 25 divided by 10, right? Do this, just the inverse of this. It's 50% past the -2 tick mark in the negative direction, right? Minus 2.5. And so you would use that percentage to and apply that to, you take whatever your actual millimeter distance is on your page between the tick marks and put that tick mark, that minor tick mark, where you want it. Okay, now let's look at the logarithmic scale. And I wanted to go through the linear scale just like we did in detail, because there's going to be a lot of parallels to how we just talked about the linear scale with the logarithmic scale. The way we just broke down the linear scale is going to be very similar to what we're going to do here with the logarithmic scale. Okay, so to start with the logarithmic scale, what we do is we draw the major tick marks, and they're going to be equally spaced, just like we did for the linear scale. They don't have to be the same spacing. They can be whatever spacing we want, but they're going to be equally spaced, which is something that people often forget about. The minor tick marks don't have to be evenly spaced, but for both the linear and logarithmic scale, the major tick marks are equally spaced. So, okay, here's the 0 point. So let's see, we can do like that. Something like that. So, if you were doing this precisely, you'd want to really measure it out, get them equally spaced. Okay, so now the main difference between a linear scale and a logarithmic scale is that with a linear scale, we have a common difference, which you can look at as the how much you add or subtract when going between major tick marks. But on the logarithmic scale, we're going to have a common factor or a common multiplier. The term I'm going to use is a common base, and because we're thinking about the base of a logarithm, I'm going to call it a common base. But the idea is when you go from this tick mark to this tick mark, you add 10. When you go from this tick mark to this tick mark, you add 10, right? Okay, but here, when you go from this tick mark to this tick mark, we're going to multiply that common base by whatever the value is at this tick mark. When we go from this tick mark to this tick mark, we're going to multiply that common base. If we go the other direction, when we go from this tick mark to this tick mark, we're going to divide that common multiplier, that common base, common factor. Okay, but now just like the linear scale, we could choose this common difference to be whatever we want. Here we can choose the common base to be whatever we want. Now, what's most commonly used is base 10. But again, you can use whatever base you want. But to start out, let's look at base 10. So, like, okay, if this is 10 here, then when you go from this tick mark to this tick mark, you don't add 10, you multiply 10. When you go from this tick mark to this tick mark, you multiply 10. Okay, and then you go in the other direction, you divide 10. You don't subtract 10, you divide 10. So 10 to the third divided by 10 is 10 squared. 10 squared divided by 10 is 10. Okay, now 10 divided by 10 is 1. Okay, and this is the 0 point, right? And that's what's another thing about a logarithmic scale. The kind of the 0 point that corresponds to the 0 point on the linear scale, the value is 1, not 0. It's 1. Okay, and if we actually keep going below this point here, 1 divided by 10 is 10 to the minus 1. Divide 10 again. Divide 10 again. Okay, and you could see, if you kept going down the scale here, infinitely far down, you would just get extremely small numbers, so like 10 to the minus 100 or whatever, right? They would just get getting smaller and smaller and smaller, but it would never get to 0. And then when you go the other direction, it goes to infinity. So you're going from 0 but never getting to 0 to infinity. And what you can notice, though, is that there's no, you can never get a negative number. On a logarithmic scale, there's no negative numbers. Now, if you actually wanted to do, there is like a workaround where you could kind of use a logarithmic scale with negative values, and I'll talk about that later. But in general, just the general definition of a logarithmic scale, there's no negative numbers, right? And there's no zero either. There's no actual 0 point. The kind of the parallel is when the value is 1, that's like the 0 point on the linear scale, and then the negative values on the linear scale kind of correspond to values that are less than 1 on the logarithmic scale. Okay, but again, though, we could have done, just to point this out, we could have done base 2. So this would be 1, 2, 4, 8. 1/2, 1/4, 1/8. You could have done base 12. 12 squared, 12 cubed. 12 to the minus 1, 12 to the minus 2, 12 to the minus 3. And all of the principles that we're about to learn about how the logarithmic scale works apply just as easily to a base 12 like this, any base you want, okay? But we're going to stick with the most commonly used base 10. Okay, and now, so in a similar way to how with a linear scale, any distance, it doesn't have to be between the major tick marks, but any distance you move, I'm talking distance actual on the computer screen, on the scale itself. Any distance you move means it's a constant number you're adding or subtracting depending on the direction you're moving, no matter where you are on the scale. Well, the parallel to the logarithmic scale is that any distance you move, like this distance here, if we move this distance on the logarithmic scale, then the starting, let's say we moved up, then we multiplied the starting number by something to get to the next number. That amount you multiplied is constant no matter where you are. So if you did the same distance up here and you moved up, then you're multiplying this starting number by that same exact number to get to the next number. And it's similar if you go down, it's dividing. Okay? And then, but, on the linear scale, if you're going from major tick mark to major tick mark, it's the common difference. You're adding 10 or subtracting 10. Here, if you go from major tick mark to major tick mark, you're multiplying 10 or dividing 10, or whatever the common base is. Okay? Now, again, on both of these scales, the major tick marks are equally spaced as far as like dimensions on the page for both of these. But the minor tick marks, you can lay out however you want. They don't have to be equally spaced. But on a linear scale, why would you not equally space them? I mean, it has to be some really special case. However, on a logarithmic scale, it actually is beneficial to have them unequally spaced, right? If we look at, here's a blank logarithmic graph, and, actually both the vertical and the horizontal axis are laid out logarithmically. That doesn't have to be the case. You could just have the vertical axis logarithmic with the horizontal axis linearly spaced, or vice versa. But here, both of them are logarithmic. But you see, the major tick marks are equally spaced, right? But the minor tick marks aren't, and it's done that way for a specific reason. But just like the linear scale, you could make the tick marks equally spaced if you wanted to. It doesn't matter. You could do whatever you want. Okay, so how does this work? Well, why are these unequally spaced? How do you interpret where to put tick marks based on what the scale value is? Well, it's just like we did with the linear scale. Okay, we plotted y is equal to 10 times x. What are we going to plot for the graph we need for the logarithmic scale here? Well, okay, 10 times x, that represents common difference, because when you go to the first tick mark, you've added 10. 10 times 1 is 10. When you go to the second tick mark, you've added another 10. So you have two 10s. 10 times 2 is 20, right? When you go to the first negative tick mark, you've subtracted 10. 10 times negative 1 is minus 10. So what's going to correspond to, when we get to the first tick mark, we've multiplied 10. And then when we get to the second tick mark, major tick mark, we've multiplied another 10. That's going to be 10 to the x. So let's plot y is equal to 10 to the x. Okay, so here is y is equal to 10 to the x, and I have it zoomed to where we can clearly see the distribution going from the origin to the first tick mark, the first major tick mark. And that you see that corresponds to, for a line like y is equal to 10x, that line passed through the origin. So the tick mark was marked 0 to the value of the function at x is equal to 1. Here, the tick mark is at the origin, it's marked as 1. And then at the first tick mark, it's going to be marked as 10. Okay? So it's the exact same idea. If we, let's bring out the ruler here. Okay? It doesn't matter, you know, this graph here, this is going from the first tick mark or from the origin to the first tick mark. So it doesn't matter how many millimeters we drew the major tick marks. This is gonna give us like a percent, right? Because the major tick marks are going to be equally spaced. So but it's the same concept. To make it easy to read, we might want to do something like, so here let's put the minor tick mark for 2 and 3 and 4 and 5 all the way to 10. So how do we do that? Well, okay, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, okay, 1 is at the origin. So, okay, here's 2. So that's going to go, let's see, 1, 2, 3, 4, 5, 3/5 of the way. Or no, wait. That's 30% of the way to the first major tick mark. Right? Now, how would you get that number? Because, I mean, I got that number because I'm looking, I can see this is spaced out into 10 equally spaced pieces, and we've gone 3 of those spacing, so I know it's 30%. But if you didn't know, if for some reason you wanted to plot a tick mark for 2.25, well, what you do is, just like we did with the linear scale, you just use the inverse, which is the logarithm. You say the log is saying 10 to what power is equal to, and if we'd say 2.25, right? And that's what you're asking. You're saying, you're trying to figure out 10 to what power this x value is going to give me this. And so you get a value, and you know, okay, that's giving you that percent between, it's 0 point something, 0.4 something, whatever. That's the percent between the 0th and the first major tick mark, right? But let's see. If we do 2, that's y is equal to 2. That would be 30% of the way. So you would, if this is, what was this? It looks like, I didn't measure this one, so I don't know, 19 millimeters. So I would do 30% of 19 and then do that many millimeters and mark off the tick mark, and that would be 2. I put that as 2. Okay. 3 would go here. 4 would go here. 5. There's 8. 9. And then 10 is the major tick mark. And that's how you would space them. And so if we look, you see that's exactly how these are spaced. Now, this is actually set up. This paper here is set up for base 10, and most of the logarithmic scales that you'll find are going to be set up for base 10. It's set up in the sense that, like, well, you could use any base you wanted here, and it would work fine. But only base 10 would work out the way these are spaced, to where you've got that nice, you know, if this is 1, you've got 2, 3, 4, 5, 6, 7. If you did it with another base, you would measure off and see, okay, what percentage of this is this down from between the first and second tick mark, and you'd plug that in. So how would you do that? If we measured this and we got that this was, we got the total distance in millimeters, right, with the ruler, and this distance, and we saw that it was 26% of the way. This was, so if this was the 0th, okay, let's do it this way. Let's say we went from this was this was 1, this was the base to the first power, this is the base to the second power, and let's say it's not necessarily 10, and so we were in between these two, and we got a measurement, and it was, we wanted to see, okay, going to 38% of the way from this tick mark to this tick mark, 38%. What would we be, how would we get what this value corresponds to on the scale? Well, okay, in that case, we know the x value. It would be like 1.38, right? So let's say we were right here. That's 1.2. That's 20% of the way from 1 to 2. Well, you're just plugging in 1.2 into the function. If it was base 12, it would be 12 to the x, and you get what the value is. If you're going in the other direction, if you knew the value, like if this was base 12 and you knew the value that you wanted, but you wanted to find it, like, okay, what's its percent position, then you're doing log base, whatever the base is. And to get the x, that base to what power is equal to the value I'm looking for. And you would get, maybe you got 2.48. That means you're 48% of the way from the second tick mark to the second major tick mark to the third major tick mark. Okay, and again, though, these are spaced out. You'll most commonly see the tick marks spaced out for base 10, but if you plotted base 12, it's no problem to mark off what these tick marks are. It's just probably not going to be nice, clean numbers. And, actually, if you're going to do base 12, you might want to put, the number of tick marks to where you could count 1, 2, 3, all the way to 12. Here, you can't, you're not going to count right anyway. 2, 3, 4, 5, 6, 7, 8, 9, But there's no, like, official rules. You could make evenly spaced tick marks with a base 10 or whatever. But what's going to happen is those evenly spaced tick marks, you're not going to have clean numbers. But you could absolutely do a base 12 or whatever and do it into thirds. You would say, okay, 12 to the 1/3 power is equal to what? You put that number. 12 to the 2/3 power is equal to what? You put that number. If you were between 12 to the first and 12 to the second, it would be 12 to the 1 1/3 power is equal to what? 12 to the 2 2/3 power is equal to what? Okay, but now again, though, just like the, I'd mentioned with both the linear and logarithmic scale, once you just need to draw the tick marks for between the minor tick marks between one interval of one major tick mark interval, and then you can just copy and paste that to all the other intervals, right? You'll have 2, 4, 6, 8, 10. Copy and paste that same spacing. You'll get 12, 14, 16, 18, 20. And it's the exact same thing with the logarithmic scale. Okay, well, why does it work out that way? Because it's because it's that common difference. This exact same spacing is going to result in, when you come up here, you're going to go that same distance, you're going to add 2, 12. Same distance, add 2, 14, right? And it's the same thing when you look here. If you had, so let's look here. Okay, you go, if this is 2, okay, that means that when you went from here to here, you multiplied the starting number by 2. So no matter where you are on the entire logarithmic scale, when you go this distance, like in millimeters on the scale, you're multiplying the starting number by 2, or if you go in the other direction, dividing by 2. When you go from here to here, so we multiplied 2 by 3/2 to go from here to here. To go from here to here, we multiplied 3 by 4/3. Okay, and so now if we come here, going that same distance, multiplied by 2. Going that same distance, we multiplied by, what was it? It was 3/2. Multiply 20 by 3/2. What happens? That's 10 times 3. That's 30. See? So you can just copy and paste that spacing that you created all the way up and down the scale. Okay, and as I mentioned, the majority of the time, if you see a logarithmic scale like this, then it's spaced out for base 10. And that just means that it's not that you can't use another base. It just means that that's going to give you the 2, 3, 4, 5, those nice even numbers counting all the way from 1 to 10. Now, you might be wondering, well, couldn't I potentially use, I couldn't use base 10, but I could do like base 100. Base 100 is a factor of 10, so maybe like base 100 would work with this kind of paper. I would still get that even spacing counting all the way to 10. The answer to that, if you think about it, is no. This would only work out this way, where you give a nice even count going all the way to 10 for base 10, and that's it. And why is that? Well, because we see here that if you put in a different base, you're going to be changing from y is equal to 10 to the x to something else. The only way you get, there's no other base where the curves are going to, the exponential curves are going to line up exactly going over the interval. Right? If I plotted y is equal to 10 or 100 to the x, yeah, it's going to start at x is equal to 0. It's going to be 1, but then it'll do something like, I don't know, it'll be a lot steeper going to 10. So you're not going to have, when you put, okay, at 2, you're here. At 3, you're here. At 4, you're here. It's totally different. So if the base is different, the spacings are going to be different. Okay, so now that you understand what a logarithmic scale is and how to make one, why do we use it? When do we use it? In what circumstances do we use it? I've been mentioning that sometimes you have, here's a log plot. There's also semi-log plots. Here the vertical scale is logarithmic, but you can see the horizontal scale is linear. And it could be reversed. Maybe the horizontal scale would be logarithmic and the vertical would be linear. So why would you even use a log scale at all? And then furthermore, why or when would you use a semi-log plot? Okay, there's two main reasons for using a log scale. And the first reason, what we're about to go over here, is really the more primary reason. Let's take a look at an example. All right, shown here it's some data for 8 earthquakes. Here's earthquake 1, earthquake 2, earthquake 3. And in the first column this is an intensity measurement. And this is like measured with a seismograph. And it's just, these numbers are representative of the energy level of the earthquake. And, I'm not sure exactly how they measured or what exactly that measurement corresponds to, but this is what they use to correlate to the energy level of the earthquake. And this here is like a raw physical measurement from nature. So in that the scientists feel this is the best measurement, that it's most representative of the energy level of the earthquake. And so the scientists are at the mercy of whatever nature gives them, right? This isn't a definition. I mean, it's a definition as far as they feel like this is the best parameter the best measurement to use. But as far as what the measurement, the numbers come out to be, they don't know. Okay, so, and now what this third column is, let's ignore the third column for the moment. So, okay, we have 8 earthquakes, and we get these intensity or energy level measurements. So let's say we want to plot these. And what we'll do is we'll make a simple bar graph. So we've got, okay. So let's do, okay, this will be 1, 2, 3. Okay, so that's earthquake 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is the earthquake. This isn't a scale. This is just the number of the earthquake, right? There's really only one data point we're plotting, the intensity. So, okay, without a logarithmic scale, what we would do is we would put a linear scale here vertically. And what I'll do is I'll say, so we see that we have a lot of big numbers here, 10 to the 4th, 10 to the 6th, 10 to the 8th. Well, okay, we can use metric prefixes. to make this simpler. So we could say maybe this is, whatever the energy units are. I'm just making this up. This might be incorrect, but let's say the energy units are in joules. So this would be megajoules. So in that case, this would be 1.58 megajoules. This would be 126 megajoules. Okay, so there we go. Now, the next thing we would do is we would look and see, okay, what's the largest value here? Well, here's a 10 to the 8th. So we could do, we could just do this. We could say this tick mark here, leave a little space at the top, and then we'll do 10 to the, well, that's not 10 to the 8th. It would be in megajoules. It would be, well, we could do this actually. I'm not going to leave a space, and I'll put 200. That's 200 megajoules. So that's 2 times 10 to the 8th. Okay? So that's the largest value. And then we might make the origin here not 0. We could make it something else, bring it up a little bit, but let's see. The lowest value is 63.1 joules. So, let's just make this 0. Okay? So, because 63.1 is pretty close to 0. So, okay, so now what we do is we draw some a tick mark in the middle. That's 100. Then we'll do some quarter marks. So 50, 150, and then we could do some eighth marks. So 25, 75, 125, 175. Okay, so let's plot these. Let's go ahead and start with the biggest earthquake. Why not? So 1.26 times 10 to the 8th, that's 126 megajoules. So that's the third earthquake. So that's going to be, we'll come up here somewhere. Let's see, 126. So let's see, this is, it's still probably be right past 126. Couldn't even really see how far past. So like that. Something like that. Okay. So yeah, probably I could have made this. That's the largest earthquake. I probably could have made the top a little bit lower. Maybe made this 150, but okay, but it's fine. So, all right, 3.16 times 10 to the 7th, that's 31.6 megajoules. So 25 and then 12 and a half is like 37. So, you know, the sixth earthquake is somewhere around there, I guess. Okay, what's next? 1.58 times 10 to the 6th, so 1.58, 12 and a half, and then 6 and a half. I mean, so we're not even going to be able to see this bar. It's, you know, something like that. Well, okay, that we have a problem. That was the third largest earthquake. Every other earthquake, we've been going in order from largest to smallest. Every other earthquake is going to get smaller. So this plot isn't going to work. And, you know, okay, well, maybe I could have made this, you know, the top 125. Well, that wouldn't have mattered. I mean, I guess it would have pulled this up a little bit, but I mean, we had 5 more earthquakes to go. That's not going to help at all if I made the top 125. Okay? So what would fix this issue is if we made this a logarithmic scale. That would fix the problem. Okay, so we'll plot that in a second, but what exactly is the problem here, though? Because a lot of people have a misconception about how to describe what's happening here. All that's happening, this issue is coming up for one reason. If you take the data set, all of the data points, and you compute what the range is. So remember from statistics, the range is the largest value minus the smallest value. If that number is a really big number, you're going to have this issue. Now, just a note, I'm not referring to if, you know, you have some data sets and the numbers aren't that different in magnitude, but you have one point that's way off, and you look at that as like an outlier, so you might eliminate that from the plot. In that case, no. I mean that once you've eliminated any outliers, you have a data set and you've eliminated outliers, and so every single data point is just as relevant as the others. Then if you compute the range of the data set, the largest value minus the smallest value, and it's a really big number, you're going to have this issue. Now, okay, maybe if you had a data set like this and you didn't consider this one point an outlier, it was actually relevant, maybe you could make a plot of just these points and put like a note off to the side of what the value of this data point was, okay, then you don't need a logarithmic scale. But you get the idea. In general, there's no simple way around it to where you can just kind of note what this one data point is off to the side, or like eliminate it as an outlier or something. You have all relevant data points in the data set, and they all need to be plotted on the same graph. Then if the range, you find the range, if it's really large, you're going to have this issue. Okay, now note that this isn't something we can use a metric prefix to fix, because that's what we typically do when we have really large numbers or really small numbers. Then instead of having to write these big values, we can use a metric prefix. That's not an issue here. We used a metric prefix. The problem was we had one value that was 63.1. It didn't even need a metric prefix. You had another value that was 794 that didn't need a metric prefix, and then another value, 1.26 times 10 to the 8th, that needed a metric prefix. But the problem is, though, that these are all, they belong in the same table. Right? There's no, like these are, you're just measuring earthquake, this data, you're taking this measurement from earthquakes. These all kind of mean the same thing. You don't want to separate these. These are all going to have either no metric prefix or all the same metric prefix. You want to look at these on the same plot. It doesn't make sense to separate these. Okay? And so with that, another misconception people have is that, okay, let's say you have a really large number at one, around 10 to the 8th, and then one around 10 to the 1st. Well, if you've got a nice kind of even distribution of data points all the way through the range, then you're not going to have this issue here, right? It's only like if we had a few data points really large, and then another group that's really small, or not really small, but like just a big difference, because like I wouldn't say 63.1 is small necessarily, right? But you have a group up here and then another kind of group down here, this big separation in magnitude, then the issue comes up. But if you had a nice kind of distribution of data points all the way down that range, then this issue doesn't come up. No, that's incorrect. Because look, we actually have a nice, 10 to the 8th, 10 to the 7th, 10 to the 6th, 10 to the 5th, 10 to the 4th. 10 to the 2nd, it's kind of a nice distribution of points. That doesn't matter. It's all about if you've got any points, any 2 points that are really big difference in magnitude, but they belong with the same units and on the same plot, then you're going to have trouble plotting it on a linear scale. And then you want to consider using a logarithmic scale. And most often base 10, but if you need, for some reason, you could use a bigger base if you need if they're really spread out. Or maybe you don't need as big of a base as 10, okay? And so that's the primary reason why a logarithmic scale is used. Now, there's another reason, and I'll talk about that in a little bit, but this is the main reason. So let's go ahead and replot this with a log scale. Okay, so you use the exact same logic to set this up as you did with the linear scale. You put let's say these are all major tick marks, okay? So you evenly space the major tick marks. Even here, we've got, okay. And you just, okay, what's the smallest number here? Well, we go all the way down to 63.1. That's pretty close to 1, so I'll put this as 1 down here. But, there's plenty of applications, like when it comes to the pH scale. The hydrogen ion concentrations vary from like 10 to the minus 14 to all the way up to 1. Well, then you'd start at 10 to the minus 16 down here, right? So this issue could, with having this data set with a large range, it could come up with, maybe you have really small numbers, like 10 to the minus something, 10 to the minus 20, 10 to the minus, whatever. So, and the logarithmic scale works for any kind of large or really small number, right? You could go as far 10 to the minus whatever you want, but we're going to start at 1 here, and then let's see, let's do base 10. So we'll do, let me do this. 10 squared, 10 to the 4th, 10 to the 6th, 10 to the 8th. And yeah, that'll work. And this is in joules. Not megajoules, we're just leaving it as joules. So, all right. Now, okay, yeah, normally I'd want to make the tick marks the right spacing, but I'm just going to do this like a rough plot here just to show you how it's going to fix the graph issue. And the fact that it's not going to be lined up precisely with the minor tick marks doesn't matter. So, all right, the largest earthquake is 1.26 times 10 to the 8th. That's number 2. So, okay, right in there somewhere, 1.26, a little bit past this major tick mark. So, all right. Okay. Or wait, no, that's earthquake 3. That should be earthquake 3. Something like that. Okay, earthquake 6. 3.16 times 10 to the 7th. So, somewhere there's 10 to the 7th. 3 would be kind of in the middle, I guess. Okay, now earthquake 2, 1.58 times 10 to the 6th. So, something like that. Okay, earthquake 7, 6.31 times 10 to the 5th. So, maybe here's 10 to the 5th. So 6 is, somewhere in there, I guess. Okay, earthquake 1, 2.51 times 10 to the 4th. Here's 10 to the 4th. So 2 is maybe, like that. Okay, 7.94 times 10 to the 2nd. Earthquake 5. Like that. And then 1.58 times 10 to the 2nd is just right past 10 to the 2nd. And then earthquake 8 is 1.58. Or wait, no, that was earthquake 8. And then 6.31 times 10 to the 1st. So 63.1. Okay, yeah, and there you go. See, problem solved. So again, that's the main reason you use a logarithmic scale, what I just illustrated. But when do you use like a semi-log scale, right? So you have one scale is log and the other scale is linear, right? When do you use something like this, a log-log scale? Or here's a semi-log scale, log here, linear there. Or talked about it at the beginning of the video, even a 3D Cartesian coordinate system, if you could choose all 3 of these to be a log scale, just one to be a log scale. So how do you choose? Well, the simplest answer to that is, so if you're going to have, if it's 2D, you're going to have two sets of data points. If it's 3D, you'll have 3 sets. So like that's like you'll have the x variables, the y variables, the z variables, right? You'll have every single, if it's 2D, you're going to have an x and a y. This was really 1D because I wouldn't consider this, I don't know if I could look at that as I guess that is kind of an x variable, but let's say like these numbers here actually meant something. It was an actual measurement, right? Well, okay, then you have an x and a y, and so each point would have an x and a y variable. And if it was in 3D, same idea. You'd have each point would be have an x, y, and a z variable. That would be tied together. Well, all you would do is you would like separate all the x points off on their own. Separate all the y points off on their own and the z points off on their own, and do an analysis just like we did here. If you take those points by themselves, can you like plot them on a bar graph with a linear scale and you get a good visual of all the points? Well, then you don't need a log scale. If you can't plot them, if you need a log scale to plot them and see and get a good visual, then you're going to need to use a log scale. And that's it. Simple as that. So you bring those data points, all the x, the y's, and the z's off to the side. If only the z's need a log scale to like visualize them, then you just change z to a log scale, whatever base you want, and leave x and y linear. Or maybe you need all 3 to be a log scale. Okay, now there's also something referred to as logarithmic units. What does that mean? Well, that's referring to something like what's shown here. This gives the magnitude of the earthquake. Okay, and logarithmic units are, it's pH is also, that's a logarithmic unit. Decibels is also a logarithmic unit. And for the exact same reasons that magnitude is a logarithmic unit, right? The unit here is decibels. The unit here is pH. Not sure what this would be called, like this is the Richter scale. I'm not sure what they call this unit. And all it is they want a way to communicate. The scientists want a nice way to communicate how strong an earthquake is. But these numbers are, they're it's hard to, these numbers are so different in magnitude, you can't just use metric prefixes, right? You could, metric prefixes, if you put a metric prefix, you get nice, this would be 1.58 megajoules. That's nice. Well, you can remember 1.58. Here this would be 31.6. Yeah, you could work with that, but when you get too small, it doesn't work. So they want a nice way to communicate how strong an earthquake is. And this is the measurement that's best representative of exactly how strong an earthquake is. So what they do is they invent they define a new number, they give it a name, and they're saying, okay, the magnitude of the earthquake, which is representative of how strong an earthquake is. When we're talking to each other, when we're telling the public is communicating we're communicating with the public, and the public is communicating with themselves about how strong an earthquake is. We're not going to talk about this number here. That's too complicated. We're going to make up another number that's still representative of that, but that's going to be the logarithm of this intensity value. And that's what this number is. You take the log of this number, you get this. The log of this number, you get this. And so this is the Richter scale here. This represents the magnitude of the earthquake. And it's just another way of saying kind of what it's representing what the energy level is. That's how the magnitude is. That's how you want to say how strong an earthquake is, right? The energy level. Okay. Now I'm pretty sure you can't into a logarithm. You have to input something unitless. And so I know it's like you're inputting joules into a logarithm, but this isn't exactly correct. I'm pretty sure that the way they input it, it's like the actual intensity of the earthquake divided by some reference level intensity that represents like a 0 level earthquake. And so the units of the energy cancel, and you have some unitless number in the log. So, yeah, just don't worry about it. This all might not be exactly correct per how the Richter scale works, but you get the general idea. So that's what logarithmic units are. Okay, a few more things to talk about. I still need to tell you the second reason log scales are used. But first, so it's important to note that here we have a log-log scale, and if you plot a power function, so a times x to the m, on a log-log plot, it comes out linear. You get a line. Okay, and so now you could think about, you could shift this up or down, shift the x to the right, transform this in any way, and it's still going to come out linear. But let's keep it simple and keep it basic like this, just to make it easier to illustrate to you why it comes out linear. But and also remember that if you think about any polynomial, what this is like the end behavior of a polynomial, of any polynomial. So the end behavior, it takes the form of the leading term, right? So if you had a fifth order polynomial, then at the end it's doing something like this, right? So that's what this is. It's like the end behavior of a polynomial. So, okay, let's take the logarithm of this entire function. So we've got log of y is equal to log of, okay, now we can use properties of logarithms to separate this into two separate logs. Okay, now we can use properties of logarithms to bring this m out front. Okay, so now there we go. If we take a look here, if we plotted on just a linear a linear plot, if we plotted log of y versus log of x, that's going to come out to be a line. A line with slope m and y-intercept log of a. And so when you just plot, that's why if you just plot this as it is on a log plot, it comes out linear. Because in a sense, that's effectively what you have. You on a log plot, you have like the log of the y variable and the log of the x variable. Now, you might be wondering, well, no, we don't. It's like 1 and then 10 to the first and then 10 to the second. We haven't taken the logarithm, right? If we took the log of this, we'd have 1, or no, this would be 0, 1, 2, 3. Well, the way you have to think about it is we've kind of forced an exponential distribution onto, at the end of the day, it's still linear, right? This is still equally spaced major tick marks here. To actually plot a true exponential distribution, we'd have to have a really tall piece of paper. And that's why if you plot this power law here on log paper, it's going to come out linear. Now, we did log base 10 here, the common log, but the properties of logarithms apply for any base log, and so this will come out linear on any log plot. It's just depending on the base you use to set up the graph, it's going to change the y-intercept, and the m wouldn't change, but the slope of the line would still, I would think, would be different because the points you plot would be different based on what exactly is the value at the first tick mark, second tick mark, etc. But again, no matter what base log system you set up the plot as, a power function is going to come out linear. Okay, now on a semi-log plot, if you plot an exponential, so a times b to the x, the exponential is going to come out linear. So x is a linear scale, y is a log scale. Now, why does this happen? And, this is base 10, but it could be any base. So let's take the log of this entire equation. So we've got log y is equal to log of, okay, now using properties of logarithms, we can write this as, okay, now once again, using properties of logarithms, we can write this okay, so now you can see here, if we plotted this on, we had log of, this is a linear scale, log of y versus x, this is going to be a line, because you have log of y, x, with this, the slope's going to be log of b, y-intercept log of a. That would be a line, and so that's why if you had a log scale with the vertical scale being a log scale and the horizontal scale being linear, an exponential comes out as a line. Okay, the other reason that log scales are used is because they preserve rates of change. Or I don't want to say that. They preserve percent rates of change or percent changes. So, because I don't want to say they preserve just general rates of change. When I say rate, that doesn't mean we have to have time. Just the, so if we have a linear scale, y versus x, you could have, it's inherently linear. So the change in x with respect to change in y is constant. So in that sense, the rate of change is preserved. But let's say you had a situation where you were plotting on a linear scale something like the revenue of a company versus time. Again, I'm saying rates of change, but it doesn't mean you have to have time. It's anything. Any kind of change in the y with respect to the change in the x. Okay, so the revenue versus, let's say this is years. So years after a certain 2000 or something. I don't know. So, here's 1 year, 2 years, 3 years, 4 years, 5 years, 6 years. And let's say this comes out linear. So that's good, right? the company is growing. Every year, the revenue has increased. Right? Over the course of the year, the revenues, you're getting more and more revenue. Well, the company, it might want to look at this not from a percent rate of change. A percent rate of change is it's like the change in a quantity like revenue over the starting revenue. Because if you think about it, let's say you have Walmart has an increase in revenue over the year, and a small business has that exact same, like a Walmart all Walmart as a corporation, all of the Walmarts has a change in revenue over the course of the year, an increase in revenue, but a small business has that same increase in revenue. Well, that's not the same thing, right? Walmart, it's got all these companies. It doesn't. That's not the same thing at all. So what you really want to say, okay, we had an increase in revenue, but what was the starting revenue? Okay, right? Increase in revenue over the course of a year, but what is that relative to the what the revenue was at the start of the year? Well, that's what log scales preserve. They preserve that percent change, right? A linear scale preserves the rate of change, but not the percent rate of change. The log scales preserve that, the percent rate of change. And it just has to do with the fact that it's the multiplication is it's a common factor everywhere, that common base. So I can illustrate this to you. So, okay, you have X 1 to 10 and Y, I just put in 4 times X. So, and plotted it, and there it is. There's a line on a just linear vertical scale, linear horizontal scale. Okay, now if I double click here and change the y-axis to a log scale at base 10, and there you go. This illustrates that the percent change it's actually the company, it's decreasing. So if this was like revenue, then yeah, the revenues are increasing, but the company the company is not really growing. Like if it's in other words, if it stays on this pace, eventually it's going to not the revenue is going to not increase. Okay, so that's the other use of logarithmic scales. I saw another video where it was like COVID. It was a plot of COVID deaths with respect to like the number of days since the outbreak, something like that, in the different countries. And since it was on a log scale, it didn't matter where on the scale or on the graph you were. Any kind of jump in the graph, that was, you could consider that it's the same, like the proportion was the same. So if you had a country with a bunch of COVID cases, and so they were way up the graph, but since it was a log scale, if you saw a jump in the graph and then you looked down the graph at another country and you saw that same size jump, you knew it was just as severe of a jump because it was a log scale. It was a percent change. Okay. Now the last thing to talk about was I mentioned that you could potentially think about doing a log scale with negative values. And all I meant by that was, you could just set it up the exact same way, except you're just putting, here we do -1, -10 to the first, -10 squared, -10 cubed. I mean, and just set it up the same way. It's just, it's technically it's not, you can't, you're supposed to be able to go to a log scale and take the log of this number and get like an integer, right? A major tick mark, you take the log of the major tick mark value and you get an integer, and then you go to the next tick mark and you take the log of that value and you get an integer. Well, you can't take the log of a negative number. But I'm just saying, if it's not, these are just graphical methods to help illustrate something. So if it was really beneficial for you to use negative values on a log scale, I mean, you could do it. Just put negative value, just set it up the exact same way we talked about and how it's set up, but put negative values in front of the major tick marks. Right? Now, there is an issue in the sense that, you could do positive and negative regions, but if you did that, there wouldn't be, you can't have an origin, right? You couldn't have a graph. It makes no sense to have, if you then started, let's say you did it like this. You went from 1 to -1, and then you had maybe -10 here and 10 here, something like that. And you extend it out in both directions. Well, but there's no actual origin where 0 is. You couldn't have a graph going through like that. That doesn't make any sense. So, but again, I'm saying you could do this if it was that beneficial to have a negative log plot. You can do it. It's not a big deal. These are just graphical methods to help illustrate. It's for us to be able to help illustrate relationships between variables. Okay, so yeah, that was a long video, but there was a lot to talk about. But so you should now have a good, clear understanding of logarithmic scales.